Thank you very much, Bala. Thank you. So after Ramesh Narayan's beautiful exposition of the subject of astrophysics of black holes, this talk is going to be a bit more technical, I'm afraid. I will try to tell you, give you a summary of the recent results from LIGO on observing black holes using a new tool of astronomy using gravitational waves. This discovery has been made by a large collaboration of people from the LIGO scientific collaboration and the Virgo collaborations. I'm speaking on behalf of the collaborations. So just to remind people, the advanced LIGO observatories have been have started their first observational run on the 12th of September, and it went up to 19th of January this year. So. And these are basically two large Michelson interferometers with arm length of 4 kilometers each. And there are two such observatories in the two different sites in the United States. One in the northwestern United States in the Washington state in a site called Hanford, and another in the southeastern US in a site called Livingston in the Louisiana. So these sites are essentially chosen to maximize the light travel time, the distance between the two sites. So the light travel time, or the gravitational wave travel time, is like 10 milliseconds between the two sites, so it corresponds to 3,000 kilometers. During the science runs, basically, which is the first science run following the upgrade of the LIGO observatories to the advanced LIGO configurations. They had unprecedented sensitivity towards gravitational waves, or the frequency range of about 20 to 30 hertz to a few kilohertz. So this is, for example, the strain sensitivity, the noise in the detector calibrated the units of metric perturbation, or the strain due to gravitational waves, in the frequency band of 20 to a few kilohertz. And as you can see, the best sensitivity is around a few hundred hertz, which could be just as low as 10 to the minus 23 in dimensionless units. So during this 4-month-long science run, two confident detections of gravitational wave events were made. These were termed GW150914 and GW151226, following the dates of the events. One is 14 September, another is 26 December in 2015. And there is a third, these are highly confident detections, what physicists call the 5 sigma discoveries, which means that the probability that anything other than the real gravitational wave, noise in the detector mimicking the signal, is extremely small, of the order of less than, the false alarm probability is less than 10 to the minus 7. And there is a third but less confident candidate event, which cannot be claimed as a highly confident detection, which is called a LIGO Virgo trigger 151012, which basically means that it happened on the October 12th. So these events, the highly confident events, were detected by two independent pipelines that uses models of the expected signals that came from General Relativity, expected models of the compact binary coalescence. And in addition, the first event was in fact detected first by a pipeline that looks for generic transients in the data, looks for bursts that are coherent in multiple detectors, which does not assume a model of the expected signal. So it was so loud it was able, basically, even a search pipeline that was designed to detect just bursts of expected signal was able to detect the first signal. So if you want to see plots illustrating the confidence of these events, so of course we do have a large number of background events in the detector just produced by essentially noise transients produced by either the environmental as well as or events happening in the detector, such as glitches in various fundamental noise sources. So this shows the distribution of our background events. The horizontal axis is a particular detection statistic, let's say the signal-to-noise ratio. And this black histogram shows the distribution, the probability distribution of the background events in the detector. And you can see that these orange squares are the the foreground events, which are the real gravitational events, and well, which could be potentially real gravitational events. And you can see that one event stands out significantly from the background. The probability that our background can mimic such a signal is less than 10 to the minus 7, which qualifies as better than 5 sigma in the standard Gaussian standard deviations. Now, and here is the significance of the second event. So this is again the background computed after removing. Now that we have we have made a confident detection of the first event with a confidence greater than 5 sigma, we can remove it in the data and then look at the rest of the background. And again, then there is a second event that stands out, again with confidence greater than 5 sigma, which is a December 26th event. In both plots, you can see an event that stands out from the background, but with much less confidence, something of the order of 2 sigma, which is this third trigger, which cannot be claimed with very confident, high confidence as a gravitational detection. But it is more like a gravitational wave than a detector event. So from this, so there are 2 triggers, as I said. The first one is a very loud and short-lived signal that lasted in the detector bandwidth for a duration less than 0.2 second. And you can see this. This was so remarkable that even by applying a simple data conditioning the data, by applying a simple band pass filter to the data, you could see this event in the data. And this shows the best match template, or the most probable template, after comparing the data with theoretical templates. And you can see, even by eye, extremely good agreement between the data and the most probable theoretical waveform. Right, 7 milliseconds. 7 milliseconds. The third one, so the second one is about 1 millisecond. The first one was 7 milliseconds. The second one was 1 millisecond. Yes. It depends on the location of the source in the sky. So, but the second event was much much weaker and a longer duration signal. It lasts for of the order of 1 second in the detector. So which is shown here. So this is basically the data in the detector in the Hanford and Livingston after applying a simple bandpass filtering. And this black trace here is the best fit template. So unlike the first event, you cannot clearly see the event in the data by just looking at by eye. So you need to apply more sophisticated data analysis techniques, for example, using match filtering, which involves cross-correlating the data with theoretical templates of the expected signal. So if you do so, this shows the time series of the signal-to-noise ratio. So basically, this involves cross-correlating the data with theoretical templates by sliding the template in time. So you see that when using the right template and applying the right time shift between the data and the template, you get a peak in the signal-to-noise ratio time series. So the inference is that because the first event is loud and short, it must come from a massive binary black hole system. And the second event must come from a less massive, but still a binary black hole system. Because of the location of the sky, there could be 2 reasons. One is that the particular realization of the noise can be different at different times. And the location of the source, due to the location of the source, the same 2 different detectors can have different sensitivity for a given location of the source. Okay, so the most confident identification of the signals were made using searches for binary black holes or compact binary coalescence, assuming models of compact binary coalescence waveform using computer using GR. And this basically includes involves cross-correlating the data with theoretical templates, which includes the in spiral of the system as well as the final merger and the ring down of the final black hole. And so these templates were computed by combining analytical calculations from post-Newtonian theory and effective on-body formalism with large-scale numerical relativity simulations. And here we have Bala Iyer, who was one of the pioneers in the Poisson tuning calculations in GR. And so this, the data, each segment of the data was cross-correlated with something like 250,000 templates corresponding to different masses, different choices of masses and the spin of the black holes. This shows an example of the discrete choices of the masses of the two black holes, M1 and M2, that are cross-correlated with the data. There are something like 250,000 templates. And we also include the effect of the spins of the compact objects, black holes, but under the assumption that the spins are either aligned or anti-aligned with the orbital momentum. So there are 4 physical parameters describing a template waveform. And here are some examples of the best fit templates to these 3 events. So this is the GW151914, and this is the 151226. As I mentioned earlier, the first event is most likely coming from a binary, large mass binary black hole system, and the second event comes from a less massive binary black hole system. There was an extensive exercise to make sure that these events could not have been made by anything other than true gravitational waves. So both detectors were in a steady state of operation at the times of the event, around the times of the event, and absolutely no evidence was found that this could be explained by artifacts in the environment or the detector. So LIGO deploys a large number of sensors that monitor the environment, such as the seismometers, magnetometers, acoustic sensors, et cetera. So none of these environmental sensors of the order of 100,000 of them could detect environmental or instrumental disturbances that could be potentially coupled to the gravitational wave channel. And there was also an extensive exercise to rule out the possibility of signals being injected to the data. So we are, beyond any reasonable doubt, we are pretty confident that these are real astrophysical events. So this detection exercise was followed up by a full-blown parameter estimation exercise, which was used to extract the parameters of the source, the astrophysical source. So this essentially was done using a Bayesian framework by, again, comparing the data with theoretical templates and constructing posterior distributions of the various parameters. So we have various levels of precision in measuring different parameters of the source. For example, the first event, there was a reasonably good measurements of the component masses because the signal involved essentially the in-spiral, merger, and ring down the final black hole. So this shows the two-dimensional posterior distribution of the mass of the primary black hole and the secondary black holes. Use the 50% and 90% confidence regions. And these are the marginalized posterior distributions, which show that the median is something like 35 for the primary and 30 for the secondary in solar mass. And on the other hand, the second event predominantly consisted of the in-spiral of the two black holes, while the merger and the ring down was not clearly visible because that part was essentially buried in the noise. So the entire information came from the in-spiral part, where because of the degeneracy between the two component masses, the component masses was not very well measured. You had larger errors in measuring the mass of the component masses. So still the primary, the median value is about 14 solar mass, and the secondary is about 8 solar mass. But for example, certain combinations of the masses could be measured very well. This is called, one particular combination called the chirp mass, which is a particular combination of the two masses could be measured very well, because essentially the in-spiral waveform is dominantly determined by this particular combination of the two masses. Although we, especially for the second event, we do not see the signature of the merger or the ring down of the final black hole, one is able to accurately infer the properties of the final black hole using, essentially using numerical relativity simulations. So the idea is that you measure the initial parameters of the system using the full waveform, and given the initial parameters, you can predict the mass and the spin of the final black hole using numerical relativity simulations. And this could be measured with, this could be inferred with quite good accuracy. For example, this is the mass and the spin of the final black hole from the first event, and the median values are about 62 solar mass and the dimensional spin of 0.67 from the first event with pretty good error bars. And the second event, the mass of the final black hole is 20.8 median value, and the dimensional spin is 0.74 with reasonably good error bars on both. All these error bars are 90% credible intervals, including the statistical and all the non-systematic errors, which is pretty exhaustive. Yeah. Yeah. Well, we are essentially measuring the initial parameters, and given the initial parameters, we can infer the property of the final black hole. Initial parameters, exactly. Yeah. So this is a summary of the accuracies of various parameters, the measurements of various parameters from this event. So, for example, the first event was quite loud, signal noise ratio of 23, and the second was a bit quieter, 13. And apart from this parameter that I mentioned, some of the interesting parameters are, in fact, both the events came from fairly close distance of 440 megaparsec. So it's actually a really hot region in the universe. But that's just a joke, of course, because they come from very different locations in the sky. So although they come from similar distances, the locations are quite different. And also the error bars on these estimates of the luminosity distance is quite poor because of the fact that the luminosity distance and the inclination angle is highly correlated. So, for example, a binary that is very far but face on to us would look very similar to a binary that is nearly closer to us but highly inclined. The similar kind of degeneracy that Ramesh mentioned is in stock of mass measurements. So, as a result, the luminosity distance measurement has large uncertainty. We are unable to measure the cosmological redshift directly from the source because the redshift is completely degenerate with the mass of the system, because a reflection of the fact that general relativity has no scale. It's completely scalable to mass. But if you assume a cosmology, you can convert this measurement of the luminosity distance to a redshift, and both for the first event came from a redshift of 0.1, around 0.1. So this is basically a summary of the first observational run of the advanced LIGO, which claimed 2 confident detections and a third possible detection. In some sense, this is an end of the era of gravitational detection, and it's beginning of a new era of gravitational astronomy. So advanced LIGO will operate its next science run with a slightly improved sensitivity in the next few months. And there is some hope that the advanced Virgo observatory in Europe would join the science run after a few months. There's a fourth detector called Kagra that is being commissioned in Japan. And we are also very excited about the possibility of the LIGO India, which was recently approved, which is expected to join this international network in the next decade. So now that we have made, the LIGO has observed a few events in the first science run, we have a much better understanding of the event rates of binary black hole coalescence in the universe. And Nathan, we will hear more about this from Nathan. So based on this, these estimates, we can make projections of what LIGO and the sisters project would observe in the upcoming science runs. And so this is, for example, such a plot showing the O2 and O3 are the upcoming observational runs of LIGO. And the horizontal axis here shows the increase in the observing time volume. You're basically the observant volume multiplied by the time period of observation as a normalized by the time volume of the first observation run. So if you increase the time volume, basically you increase the possibility of observing more events. And these shows the probability distributions of observing more than 10 or 35 or 70 events in the upcoming observational runs. So the summary is that if you look at the medians of these posteriors from the next observation run, which would happen in the next few months, we are expecting to see of the order of 10 observations of binary black holes based on this estimates. And let me stop. It's exactly 20 minutes. By showing a seems this has a problem. The last slide always. This has happened with Ramesh also. Okay, I just want to stop this by showing a nice PR image that LIGO has produced, which shows the mass measurements of black holes from various branches of astronomy. These are the measured masses of black holes using the technique that we have heard about from Ramesh. And these are the 3 events that LIGO has measured. These are the 2 component masses in the first run, which produced a more massive black hole of about 62 solar masses. Similarly, this is the second event, which basically the merger of 2 black holes, mass 14 and 8, merging to form a new black hole about 20 solar mass. And this is the third candidate event. So this is a new population of black holes that are essentially contributed by LIGO, which we hope to increase in the next several years. So thank you very much. Can you say again? Uh-huh. Mm-hmm. Right. Okay, that's a good question. So the way the data processing is done is by, so there's prior to the event itself, there's an identification of channels that are potentially coupled to the gravitational channel. And these are essentially vetoed a priori before opening the box, so-called. So, but if you remove some of the data quality cuts, what happens is that, our sensitivity will be much worse, because there will be a large number of instrumental events that would potentially produce loud signal-to-noise ratios. But these are removed a priori before looking at the results of the binary black hole searches. So there's a vetoing strategy which is done before doing the search. It's basically removing the essentially not looking at certain segments of data which are known to be corrupted to the instrument or environment. No. These are basically cuts, data quality cuts. So you discard the data from times where you know that to very high confidence that these are corrupted by environment.
I was just wondering that this is a massive spinning black hole. The spin is like 0.73.
Yeah.
That all these such black holes have jets.
Yeah.
Is that all happening in some more sterile environment?
Yeah, so unfortunately, because the binary has been spiraling in for millions of years. There's a giant vacuum cleaner that is clean the environment. There's a mic if you want.
So I noticed that the first event, the 30 plus 30 black holes, it was right at the top end of your templates.
Mm-hmm.
Right?
Mm-hmm.
Are people making now templates at yet larger mass? Could you have missed a few?
Yeah. That's a very good question. So if for signals from a black hole that are more massive, since they're going to be shorter and louder typically, essentially that looks like a burst in the data. So although we don't have a template-based search, it is our transient search pipelines would detect it. So that's what happened even for this the first event itself. It was first detected by a transient search pipeline. Yeah, so it's not entirely necessary to have a template-based search for such massive events. But because of the improvement in the low frequency sensitivity of LIGO that we're expecting, even these systems would be longer in the detector in the future. So there are plans to extend the high mass limit of the searches even for the template-based searches.
Sir?
Yeah.
Sir, I couldn't understand what is time volume and why normalized time volume was used as a
Right. So the idea is, given now you are able to basically see a volume of the universe that has basically a horizon of, let's say, a gigaparsec. You can basically able to see binary black holes happening at a volume of your nearby universe that has a radius of gigaparsec. Now, there is certain even astrophysical events, such as mergers of black holes, are happening at certain rates in the universe. So if you observe long enough, you will see one of them. So that's why it's a product of but at the same time, even if your observational time is short, but if your horizon distance is much larger, there is a larger probability of engulfing more events in your observation. So that's always a product of your actual spatial volume times the observational time.
So the second detection that was made lasted longer. So does it help put any kind of constraints on general theory of relativity?
It's a good question. So you'll hear it from Nathan's talk. It has actually helped to putting better constraints on the so-called post-Newtonian coefficients or deviations in the post-Newtonian coefficients.